Hello, my name is Breno and I would like to present this framework to generate high-quality animations of high-energy particle events. I am the main contributor to this project and received key advice on contributions from Rafael and Lucas. This presentation is organized as follows. We begin by briefly mentioning project objectives. Then, we dive into some technical aspects where Python code is used to interface particle kinematics data with Blender 3D, a modeling and animation software. Once the basic classes are described, we show how these were adapted to animate events observed by the Alice experiment. Finally, we show selected animations which are available on the project website for anyone to use. Our main objectives are to create a framework to animate high-energy physics events and generate sample animations ready for use in outreach and educational purposes. Each event can be animated by a list of particles kinematics and a propagation model corresponding to the experimental setup. All of the code that generates the animation itself is written in Python, an object-oriented programming language. Its use of classes and objects makes it easy for users to implement animations for other experimental setups, such as the functions to generate detector structures and diverse track propagation models. Python scripts are capable of accessing the full Blender interface, allowing us to programmatically configure the scene, animate, and render the final movie. This ranges from adding detector geometries to creating spheres that represent the particles, tubes that represent trajectories, and cameras that present different perspectives for a given event. One of the fundamental classes of the program is the animationDriver class. Its member functions are called to configure the video's duration, frame rate, output path, and resolution settings, as well as to determine the simulated time of the event, which corresponds to how long after the particle collision the animation will show. The DataDriver class is derived from the animationDriver class to actually implement the animation from a given kinematic data list. We also implemented a DataDriver derived class called genDriver, which generates events with dummy distribution. This class is used mainly for development purposes and can be used as a template for implementing more realistic generators. The image at the bottom displays how the input data should be arranged inside the file passed down to the DataDriver class. Each line corresponds to a different particle to be represented in the animation. In the first three columns, we have the x, y, and z coordinates of the particle's initial position in meters, followed by its mass in giga-electronvolts per c² and its charge in units of elementary charge. The last three columns hold the x, y, and z relativistic linear momentum values in giga-electronvolts per c. All of the collected data is then passed down to a particle object, which is a base class whose variables include the initial position, charge, and mass. It also defines the particle's type from its mass, as long as it is an electron, pion, muon, proton, or kaon. Since particle propagation is utterly dependent on the experimental setup, different propagation models are implemented in classes derived from the base particle class. The particle propagator derived class presented here corresponds to a simple helix track propagation model suitable to describe charged particle trajectories near the central regions of the Alice detector. Unfortunately, decays are not implemented yet. The framework is already fully functional to animate events observed in the Alice experiment of the Large Hadron Collider. ALICE stands for a Large Ion Collider Experiment, and it was primarily designed to investigate the state of matter called quark-gluon plasma. Besides the helix track propagation model described earlier, we have implemented classes and functions to include specific parts of the detector's geometry, as shown in the image. In order to animate events, someone needs data. To ensure a framework that's usable by anyone, we resort to Alice data available at the CERN's Open Data Portal, which is an open online platform that contains data files from particle physics. One can filter these files by dataset, experiment, year, file type, collision type, and collision energy. Once a filter is applied, the user must select a given sample of files. In the case of the Alice experiment data, the available files have a .root extension. They are called the Event Summary Data Files, or simply ESDs. Each sample contains an enormous list of ESDs from which the user can choose, and each of them holds information about several particle collision events. .root extension files are not all that easy to manage. AliRoot, CERN's official software for Alice physics analysis, allows us to run C++ macros in order to export the relevant particle kinematics to the table format, readable by the Python script used to make animations. All steps necessary to generate animations are synthesized in a shell script that can be run in the terminal. It assumes AliRoot has been properly installed and configured on the system and takes care of all of the steps, from downloading data corresponding to a chosen ESD file to animating the event. It includes the option to create mosaics that feature different viewpoints of the same event. The result is a uniquely identified directory containing all the rendered videos. Each event is uniquely identifiable and traceable back to its original data source. Here we can see a basic running example where the download option is set, informing the URL address of the ESD file. Animations will appear in the default overview camera. To further select the type of events one intends to animate, it is possible to set specific triggers. For instance, option minimum average PZ is used to select events with boosts along the beam direction. Further details can be seen at the project's documentation. The image below shows a preview. Although the project is fully functional, it could benefit from specific improvements. Particle decays and secondary vertexing would allow to animate certain processes to be represented in the animation, including moving cameras configured to follow a given mother particle, or specific decay channels. The project would also benefit from the integration with advanced event generators such as Pythia and Hijing. The project can be forked or adapted to include support for other experiments besides Alice. The animations generated so far are available at the project website under a permissive Creative Commons license. You can download any of the videos and include them in your material. Take a look at existing animations in our project webpage on the link shown on the screen. Whether you are an experienced professor or an eager student who wants to learn more about particle physics, you can go ahead and start animating your own selected events from Alice Open Data. You are also free to adapt the software to your very needs. After all, it is openly available under the GNU General Public License. If you intend to add support to other detectors, get in touch. We start by showing a couple of minimum bias events corresponding to proton-proton collisions at 7 tera electron volts. As for the detector's geometry, we can see the electromagnetic colorimeter in yellow, the transition radiator detector as the outer purple part. The green cylinder in the middle is the time projection chamber, the TPC, that contains the smaller purple parts, the inner tracking system. These are PB animations that contain multiplicities that vary from 50 to 2000 particles at 2.76 tera electron volts. As for the particle types, electrons are represented by red spheres, pions are green, muons are blue, protons are magenta, and kaons are yellow. High multiplicity events are Alice's main focus. As most of the time the LHC operates with proton-proton collisions, about 1 month every year is dedicated towards heavy ion programs. Let's appreciate details of individual cameras. This is the forward camera. The helix trajectories can be observed as arcs of circles in the XY plane. This is the side camera. This is the moving camera. Again, these animations are available in HD on the project sample webpage. Feel free to use them. We will be happy to know that you are doing so. And if you do, please let us know.